So in this video, we'll be talking a little more about what polar coordinates are. Okay, so if you made it to this video, I've probably mentioned this already, or you've probably seen this from me or somewhere else already, that this is what polar coordinates are. Polar coordinates are just coordinates, and coordinates locate a point in space somewhere, okay? And the way that polar coordinates work is we identify a point by an angle and a distance, okay? And the coordinates of the point take the form r and theta. So theta is a standard angle, meaning it's rotated from what we would call the positive x-axis, and r is a distance in the direction that's established by theta. Okay, so we get a radial distance and an angle. I say r is a radial distance because it's in the direction of the angle. It's going to be out somewhere, radially out from the origin somewhere. Okay, so for this angle like that, or for this point right there, that angle is, maybe like 45 degrees or so. And then r is however far it is from here to there. Okay, so it's a distance. Now, polar coordinates, we can contrast a little bit with rectangular coordinates. Rectangular coordinates are kind of the default, what we normally use as far as coordinates go, which is just like x and y. Okay, quick example. Okay, so can you plot the point that's in polar coordinates 2 and negative 30 degrees? Okay, that looks something like this. When I say theta is a standard angle, then you remember that angles are like in standard position are if we rotate counterclockwise, the angle is positive. If we rotate clockwise, the angle is negative. So that's going to be a clockwise rotation of 30 degrees. And then in that direction, like out in this direction right here, established by that angle, we'll go a distance of 2 by whatever your units happen to be. Okay? All right, so there's that point. Rotate clockwise 30 degrees, then in that direction, go a distance of 2 by whatever your units are. All right, so let's look at a few other examples then. Can you plot this point in polar coordinates? Okay, now notice I probably, now unless I give you a unit for the angle, like say 30 degrees, so you know that's an angle, okay? But if I gave you, say, two numbers separated by a comma within a set of parentheses, then you don't know if it's rectangular or polar unless I tell you. If I just say that's a point, that could mean this is x and that's y. Or if it's polar coordinates, it could mean this is r and that's theta. Okay? All right, so we'll plot the point. We'll figure out where it is. But when I say polar, all right, I would need to tell you that. It would be incomplete information if I didn't give that to you. All right, so let's look at this and say, okay, we're understanding this as r and theta, okay? And notice there's no units there. It doesn't say 2.34 degrees. This is a angle in radians, okay? Given the absence of units there, then we know that it's an angle in radians. Because if it's polar, it's r and theta. That's the theta. That's the angle. It's in radians. Now, I think that, for me to plot this point, it might be a little bit easier if I put that in degrees. So I'll say if we've got 2.34 radians, and we multiply by 180 over pi degrees, then we'll get our number that's in degrees. Okay, so I'll do that 2.34 times 180 over pi, and that turns out to be about 134.1 degrees. Okay, so we could look at it that way if that was a little bit easier for you. So let's look at, I'm going to rewrite it over here then. I'll say my point that I have is root 5, and root 5 is like 2.2 something, I think. Let's see, I'm going to do that by calculator also. So root 5, so that's going to be, 2.23. So let's say we've got 2.2 for r and 134.1 degrees for theta. So that's how I'm going to think about that point. All right. Okay, so it says plot the point. So where or how would we do that? Well, I've explained up there what it means to plot polar coordinates. Let's start with the angle, and then in that direction established by the angle, we'll go out a distance of 2.2. So 100. Now I got my protractor, and I said I'm going to do this right. You know, might as well really do this. So here's about 134 degrees, and then I'm going to go out a distance of 2. Well, how are we going to define our units? How about we'll let our units for distance be inches? Okay, so it's like right there. There's my point. Okay, I'll rotate 2.34 radians, and then in that direction I'll go a distance of 2. So that puts it in quadrant 2 of our graph right there. Okay, so I tried to, use my protractor and measure it so that it'd be as true to life as possible. I know there's probably a little bit of measurement error, but it'd get a really good idea about where this point is. Okay, so I should really say like that's 2.2 inches. Okay, just to be a little more exact. It's hard to measure 0.2 inches just kind of off the cuff like that, but there you go. All right, so let's try another one. All right, so here it says plot the point in polar coordinates. R is negative 3, and I don't think, at least in this video, I haven't told you what it means if R is negative. Let me see, I gotta adjust the light here. That's probably as good as it's gonna get. Okay, but we'll talk about if R is negative, and theta, again, given that there's no units, I know that that's radians, okay? So here's R and theta. Now, you know the conversion factor already, okay? So I'll just take that for granted, and I'll rewrite what that number is right here. Okay, so that turns out to be negative 3 for R and 31.5 degrees for theta. So let's plot that then. Okay, so I've got my graph where everything is. So let's start with the angle again, 31.5 degrees. That would establish a direction about like this. Okay, all right, so there's my angular coordinate is going to take me out in this direction. There's I'll put 0.55 radians, okay? But R is negative, okay? Now, if R is positive, we go out in the radially out in the direction that angle establishes. What do you think if R is negative? We go the other way. We go backwards. So if that was a positive 3, then I would go 3 units of distance in this direction. But if R is negative 3, I go 3 units of distance in the opposite direction, 180 degrees opposite, okay? So if I were to go 3 units of distance that way, then I would have my point, okay? Now, I used inches in my last problem as my unit, but the units will be, up to the situation. So here I'm not actually going to measure it. I did measure the angle, but let's say going out this way, it turns out, okay? The opposite direction of 31.5 degrees, you're looking at it right there. There's about 31.5 degrees. Well, that would be out here. Take me into quadrant 3. So here's my point, negative 3 and 0.55 radians. That's where that point would be in polar coordinates. Now, again, I have to tell you that it's in polar coordinates. If you are not told, if it's not indicated somehow, you don't know if that's X and Y or R and theta. You have really no way to know. So you will be told about that. All right. So let's see. Let's do some conversion. So I have a few problems where, like right here, it says this point's in polar coordinates. Can you convert it to rectangular? And this point's in rectangular. Can you convert it to polar? All right. Let's talk about how you would do that in general. Okay, so conversions between polar and rectangular coordinates. Whoops. So polar coordinates are R and theta. All right, we've been talking about that. Rectangular coordinates, that's what you're used to. I haven't mentioned it in this video yet, but that's x and y. Okay, so that's left, right, up, down. So how we convert depends on what we're converting from. So if we're converting polar to rectangular, it's pretty simple. X and y are respectively r cosine theta and r sine theta. Okay, that's polar to rectangular. If you want to convert rectangular to polar, there's some additional details to it, but here's what we can use roughly. R will be root x squared plus y squared. And we can find the reference angle of the angular coordinate for the polar coordinates with this tangent inverse of the absolute value of y over x. That will be the reference angle. And you'll have to use that to find the quadrant of theta. Now that will involve a little bit of trigonometry or pre-calculus, as you know, but let's just say in general, we'll do this, we'll get the reference angle, and then in a pretty simple way, we'll use whatever that is to find whatever theta is supposed to be. Okay, so that's just what you do. We'll see some examples with both of these. Reasons, well, okay, it's all just right triangle trigonometry and other formulas for right triangles. So for example, this right here comes from the fact that if you plotted a point and looked at how the rectangular and the polar coordinates interact, x squared plus y squared would be r squared. Okay, this and this come from the fact that if you look again at how all this fits together, sine theta is y over r. Okay, so you can see that y is r sine theta. Cosine theta is x over r, so you can see why x is r cosine theta. And tangent theta is y over x. So you can see why we could get the reference angle from theta as tangent inverse y over x. All right, so there's our formulas that we'll come back throughout the rest of the video to use. Okay, so this point's in polar coordinates. Can you convert it to rectangular? That's the easier kind of problem, I think, converting from polar to rectangular. It's just that x is going to be r cosine theta and y is going to be r sine theta. It's not that bad. Okay, so all right, it's the x coordinate will be r, which is root 5, times cosine of 2.34 radians. That's not degrees, that's radians. Okay, and then y is going to be root 5 times sine 2.34 radians. So of course we'll have to make sure if we use our calculator to do this that it's in radians. All right, so with my calculator, I got x to be negative 1.56 and y to be 1.61. So my point in rectangular coordinates is going to be negative 1.56 comma 1.61. All right, there we go, in rectangular coordinates. Now, I used this point that I had just used in the other example. Let's see, does this look right? Negative left 1.5, up 1.6. Here's where it was. And I remember I used units of inches. So let's see, left 1.5. Yeah, that's about left 1.5 and up 1.6. Okay, yeah, I could see that. I'm not surprised. You know, I know there's some measurement error, and it's hard to measure, 6/100th of an inch, but it looks about right. I'm not, it's at least consistent with that other picture that I showed you. All right, sure. So there we go. There's x and y. That's left and up, and I think those numbers fit the picture that I drew for you already pretty well. Okay, now so converting from polar to rectangular is not difficult. You just use that. Converting to polar from rectangular, that will be a little bit harder, I think. Okay, so here's what I told you so far. So we can do like this, rectangular, polar. That's how you find r and theta. Let's do r first. That looks pretty straightforward. Okay, so my r coordinate is going to be the square root of 25 plus 144, which is root of 169, which is 13. So my radial coordinate is 13. So what about the angular coordinate? That will be a little bit harder, I think. So let's do like this. Let's see, where is this point? Now, I won't draw this one. I won't trouble too much drawing it to scale, but it's about like this. Okay? We go, to get to that point, we go left 5, and we go up 12, and that would put it in quadrant 2. Okay? And theta is this, right? My angular coordinate is like that. It's an angle that's going to put me in quadrant 2. So the reference angle is right here. I'll call it angle A. All right? So you can find the reference angle by tangent inverse of the absolute value of y over x. All I'm saying is, like, tangent of this angle is 12 over 5. And then if you know that angle, you can subtract 180 minus that, and you'll get theta. So here goes. Angle A that you see in this picture right there, okay, that's going to be tangent inverse of 12 over 5. And that's going to be, well, let's see. .3 degrees or so. So I get about 67.38 degrees. So theta then, given that this point is, it's definitely in quadrant 2, theta is going to be bigger than 90 and less than 180. I can find theta as 180 minus this angle A. This is the reference angle. So before, in that formula that I mentioned, that's what I mean by reference angle. So theta is going to be about, what is that, 112.62. All right, 112.62, yeah, 62. Yeah, if you rotate 112.62 degrees, that'll put you right there in quadrant 2. It'll be like going left up, or left 5 and up 12, okay? So the radial coordinate is 13, the angular coordinate, 112.62. So, okay, my point in polar coordinates, let's give 13 for R, and then 112.62 for theta, okay? All right. Now, it may be, who knows, that because we could give an angle in degrees or radians, that you may be asked to give this different ways, okay? So let me put an or about this. So let's see. Is there another expression of that in radians? Yeah, I could convert to radians if I multiplied it by pi over 180. So I'm going to multiply by pi over 180, and I get the same angle in radians. And I could say, well, you could say it's about 13 and then 1.97 radians. Okay? Same thing. Both of these are in polar coordinates. Both of these are r and theta. It's just that that is in radians. All right. So you'll just have to, pay attention to the question or whatever somebody expects from you. They should tell you whether they want degrees or radians, but I mean, you could see that it's the same thing, right? Okay, now let's do this. There's yet still another wrinkle to this one, because that's not the only way that we can give r or theta. There's more than one way to plot a point in polar coordinates, all right? So let me, a real quick example. Let's do like this. Before I do anything else to this one, I could say something like that. Here's a point where I go 45 degrees and I go a radial distance of 1. So the polar coordinates for that point are 1 and 45 degrees. Okay. But I could also give this same point by rotating 225 and then going a radial distance of -1. Because if I rotated 45 plus another 180, that would get me in this direction, okay? So like right here, that's 225 degrees. But then if I'm established that direction right there, if I then go backwards 1, I'll still get here. Okay, so these are two different polar coordinates for the same point. So there are lots of unlimited ways that you could represent any point in polar coordinates. All right, so there, that's another example. One more though. I mean, I did say there's unlimited ways, so okay. What about -1, -135? Okay, if I rotate 135 degrees clockwise, that's like that. That will get me to the same direction. And then if I go backwards 1, I'll still get here. All right, so there's 3 ways that we could represent the same point. Now, that, depending on the question that you're doing or depending on what you see, you may have to write it different ways. So with this one, how could I write it with, like say, maybe if r is supposed to be negative, what if that's the specification? Then I could say, well, that's 112.62 degrees. If I add another 180 to it and make r negative, I'll get to the same thing, okay? So say I take 112.62 degrees and I add 180, then I'm going to get 292. So like this angle right here, that's going to take me out in that direction, that's going to be 292 degrees. And in that direction, I would have to make r a -13. All right, so there's lots of different ways that you could write the coordinates for one single point in polar coordinates. All right, so I'm mentioning it to you this way just because in the assignment the questions might be phrased in all sorts of ways, so you understand what if the angle's in degrees or radians, if r is negative or positive, how it could all correspond to the same point. All right. Okay, so I've addressed that. I've got a clear conscience about it. I told you. Let's do another one. Conversion problem from rectangular to polar. So this point, left and down, all right? Convert that to polar coordinates. This is rectangular, right? That's x and y, so it's left and down. Let's start by finding r. Remember, that's the one that's easiest to find. R is equal to the square root of x squared plus y squared. That's what our formula says. So that's just going to be 2 because that's the square root of 4. So my radial coordinate is 2. What's the angular coordinate? Well, let's again see where this point is and go about it with the reference angle. Okay? All right. So if I go left and down, that will put me in quadrant 3. And I'll get something, I don't know, maybe about like that. That's about what that point looks like. All right, in rectangular coordinates, if I go left 1 and down √3, then I'll get theta to be like so. And I get r to be like so. R is already established to be 2. All right. So what about theta then? I'll find theta based on the reference angle, this angle A right there in the triangle. And I can say tangent of that angle A is √3 over 1. So A is equal to inverse tangent of √3 over 1. And that just uses that triangle. Okay, that's this. That's what I was talking about earlier. Then I want to find the reference angle for theta. Theta being the angular coordinate for my point. All right, so I believe that's 60, but my memory's not so good anymore, so I'll check it. It's 60. Okay, so the reference angle is 60. All right, so what's theta then to take me out there in quadrant 3? Remember, in polar coordinates, the angular coordinate is a rotation from the positive x-axis. That's always how we intend to plot theta. So, well, this would be 180 and 60, so that's 240. So theta is equal to 240, right? Theta is equal to 180 plus A, plus whatever that was. Given that we know we're working in quadrant 3, whatever I found that to be, that's the way it would work. All right, so 240 degrees. All right, well, so I got it. It's 2 and 240 degrees. Okay, so my point in polar coordinates, 2 for R, 240 degrees for theta. Okay. All right. What if you need to give that in radians? Well, it's not hard to convert that to radians. Is there any other way that we could give this point? Maybe with R being negative? So think about that. How can we get the same point, but specify that R is negative? Okay. Well, so tell me, what do you think? What's this angle right there? What if I had this angle, and that establishes my direction, and then I went backwards a radial distance of 2? Well, remember, this angle is found to be 60, so that angle is also 60 in quadrant 1. So I could also say -2 and 60. All right. That's another way to plot that same point. One with a positive radial coordinate and the other with a negative radial coordinate. Okay. All right, now, so you've seen the conversions point to point, polar to rectangular and rectangular to polar. All right, so you've seen some examples of that. You'll have to allow for some flexibility on the angle being in radians or degrees. Okay, use your judgment as far as what the question asks you. Let's try something a little bit different. Okay, so here I have an equation, and I want to convert this to polar coordinates. That was a little bit sloppy for me to write it that way. I really should say convert it to polar form, because this is not one single point. All right, it's an equation, it's a graph, it's a bunch of points, and so on. All right, so polar form would be like, is there a way to write this equation with R and theta? Okay, all right, is there some way that instead of using X and Y, we could capture all the same points in whatever the graph of this is with just polar coordinates? Okay, so R and theta. That's what polar coordinates are made of. Now, first of all, I notice something about this, that this is a circle. Its center is the origin, and its radius is 3. Okay, that's the nature of that thing. But nonetheless, if I wanted to convert it to polar form, I would just meaning to convert the x squared and the y squared out of it, okay? And remember this, maybe we'll use a variation of that one. Where did I say that came from? Well, if you look at how x and y interact with r and theta, it has to be true that x squared plus y squared is r squared. So x squared plus y squared is 9. That's like immediately convertible to r squared is equal to 9. Okay? And then if I can convert a little bit further, I'll get r is equal to 3. And I think that's consistent with this. Suppose that I get this equation, r is equal to 3. Okay? That's an equation in polar form because it doesn't involve x and y. It only involves r and theta. Oh, does it involve theta? Well, it doesn't have the theta. What's that mean about the theta? It means theta can be any angle. So whenever you're working with a coordinate system and you have an equation and the other component, like the other coordinates left out of it, like if theta is not mentioned, it just means theta can be anything. Well, where are all the points that the radial coordinate's 3, but the angular coordinate is whatever you want? They're on a circle that has a center at the origin and a radius of 3. So I'll give you that. That's my equation, but it's completely consistent with that. It would have to be for it to be right. Okay, so it says convert to polar coordinates, then it says sketch the graph. All right, let's sketch the graph. It's a circle. I told you that much already, so I'm being very particular about drawing my circles. There it is. Here is r is equal to 3. So for example, it's got this point, 3 for r, 0 degrees for theta. It has this point, 3 for r, 90 degrees for theta. It has this point, 3 for r, and 270 degrees for theta. Those are some sample points, but here's the graph of r is equal to 3. All right, yeah, there's no restriction of the theta. Theta can be whatever you want it to be, but the radial coordinate, the radial distance, has to be 3. That's probably enough, right? Oh, I'm going to do one more. 3 for r, 225 degrees for theta. Yeah, no matter what the angle is, you go out a radial distance of 3. So a circle with a center at the origin has a very simple equation in polar coordinates. It's one of the advantages of polar coordinates is that some types of equations can be greatly simplified if you work in polar coordinates. That is simpler than this, but they refer to exactly the same thing. Okay? All right, so there's my equation, there's my graph. What else do we got? Let's try this one. Okay? Convert to polar form and then sketch the graph. So converting this one to polar form, I don't think that will be very hard to do. The graph will be a little bit harder. Okay, so let's do this in 2 steps then. Okay, so first of all, convert. All right, so what do we have to work with? We know that x squared plus y squared is r squared as a conversion between rectangular and polar coordinates. And I know that x is equal to r cosine theta, also as a conversion between polar and rectangular coordinates. So my conversion is initially going to look like this. R squared minus 6r cosine theta is equal to 0. All right. So in fact, that's like a total conversion. X and y are gone, and r and theta are introduced. It's now in polar form. I still would like to reduce it if I can, though. So I could do like this. I could factor out r. Okay? And then I could divide this one out. Like if I divide both sides by r, it's going to be eliminated. And I'm just going to get r minus 6 cosine theta is equal to 0. So I'll get r is equal to 6 cosine theta. All right. So there's my polar form of that equation that I started with. Okay. What about sketching the graph? Do you know what the graph of r is equal to 6 cosine theta looks like? Probably not, because we're not that far along. Okay, unless you learned polar coordinates somewhere else, and yeah, you probably don't know what that looks like. So let's explore the graph a different way. Okay. All right. Because we probably can't tell that way, and so it might be nice to know how to analyze that to figure out what this is. Okay? All right, so I'm going to give you a hint with this one, and that is that this, I think, is reducible to a circle of some kind. Okay? So if I say x minus h squared plus y minus k squared equals r squared, that in fact is the equation of a circle that has a radius of r, if that's r squared. And every circle has a radius, every circle has a center, and it has a center of h and k. So this and this number specify the coordinates of my center. Every circle has a radius and a center. So I think that's where we can end up with this one. Okay? So now let's start here again. X squared plus y squared minus 6x equals to 0. And try to get up there. So the objective is to get from here to there, because I think that's what it can become. All right. Now, what's the difference between these? Well, so mainly in the factoring. See how both of these are like x minus h times x minus h and y minus k times y minus, they're both factored. I guess the trick with this one is writing it so that it can be factored. Quick example of that. I know somewhere you've probably heard of the technique I'm about to show you, but let's say x squared plus 10x plus what would cause this to perfectly factor as a square of some kind. This is called completing the square. Tell me, what number can I put right there that makes this factor as a perfect square? Because that's what's going to happen to this for it to become like that. Okay? Well, so the whole trick is that you zero in on that coefficient, okay, 10 in my case. You take half of it and you square whatever that is. All right? So if I take 10 and I divide it in half, I get 5, and if I square it, I get 25. All right, and that number of all numbers does lead to something that factors as a perfect square. And this is going to be x plus 5 squared. And it's easy to prove that x plus 5 times itself is x squared plus 10x plus 25. I need to do something like this, okay? All right, that's called completing the square. Now, so let's do some rearrangement. X squared minus 6x. What else needs to be there for it to factor like that? Well, what's half of 6? That's 3. And if I square it, I get 9. Okay, so there. Plus y squared. Well, that's like y minus 0 squared. So it's already the way I want it. So I just needed to add in that 9. That's the trick. But I have to keep the equation balanced, so I got to add a 9 there too. All right, so here goes. X minus 3 squared plus y squared is equal to 9. And what we have then is a circle, okay, because it's of that form. Its radius or its size is 3 because that's a 9. And then the center point is 3 for x and 0 for y. All right. There we go. There we go. Now, let's do this. Let's graph this based on that. All right? Okay. So here goes. Imagine that I've got this graph. Okay. And a circle with center 3, 0, and radius 3, that's going to look something like this. Okay. Getting the origin right there. And this point is going to be 6, 0. 6 for r, 0 degrees for theta. That's a polar point. Okay. All right. So there's your graph of r is equal to 6 cosine theta. And there's one point in polar coordinates, just for reference. But otherwise, this is a circle, radius 3, center 3, 0 in rectangular coordinates. If that radial coordinate puts this distance at 6, that's the diameter of the circle, and that means right there in the middle is 3, and that gives it a radius of 3. It's entirely consistent with this, okay? All right, so good, we got that. Now we know what something like this looks like. If we're dealing with polar coordinates and we need to know what something is, we can look at the xy coordinates if it would help us, because we might be more familiar with those, okay? All right, so let's do, actually, I had, in order to do the assignment that we had, I had another one, maybe another few, but looks like the battery on my phone's gonna die. So in this one, I'll make another one, and they'll all be posted.